All right, good morning everybody. So as Scott told you, today I'll be talking about why your smartphone works even though you abuse it. And actually the real title of my presentation is Reliability Engineers to the Rescue. So what is reliability? Well, I say that something is reliable if it works as it's promised to work when it's brand new, and if it continues to work that same way over the promised lifetime. So what do I mean if it works as promised? When you buy something, there's usually a feature sheet, or what us engineers call a data sheet included. Well, it needs to do what it says it will do. And the technical term for that is specifications. So it works to specifications. Now, I said it has to work to specifications over its promised or intended lifetime. For most consumer electronics, we design them for a 10-year lifetime. But 10 years is not a magic number. It depends on your application. So if you're designing space electronics, you're going to have to design them for a 30-year or longer lifetime. And if that seems silly, I want you to consider the Voyager probe, which is now outside our solar system and transmitting images back to NASA. That was launched 36 years ago. And if the electronics had died, we wouldn't be getting those pictures and information about the outer reaches of space. All right, so this has been very qualitative, but actually reliability is something quantitative and something you can measure. It's a probability. It's the probability that your product meets specifications if used as intended over its specified lifetime. So what do I mean by used as intended? I'll give you an example that I'm going to come back to several times. When you buy a new smartphone and you start looking at the user guide, does it say anywhere, this phone will work even if you drop it in the toilet? No, so that's not the intended use. But if you use it as intended, also a lot of products when you buy them, they say, must be stored, must be used between one temperature and another, maybe minus 40 and plus 125 degrees. So if you put your computer in the oven and turn it up to 500 degrees Fahrenheit, they don't promise it's still going to work. All right, so that's an important thing to consider. They guarantee it's going to work if you use it as specified. So people who make products behave reliably will refer. Go ahead.
As an engineer, I have a rule that's even more important than all the rules.
Tell us.
Design the product never to injure the user.
Well, that's a safety issue, and we'll touch on that as well. But that would generally be one of the starting specifications. So it shouldn't injure you when it's new, and it shouldn't injure you when it's old.
Okay.
Okay. So those of us who work in reliability, those of us who can be called reliability engineers, we don't actually have college degrees in something called reliability engineering. We come from very many different disciplines, and I've listed the most common ones up on the screen. These include mechanical engineering, material science, math, electrical engineering, aerospace engineering, and physics. Now, my degrees are in electrical engineering. And those of us who have electrical engineering backgrounds and work in reliability, most of us focus on integrated circuit reliability, IC reliability. Now, ICs, integrated circuits, they're the brains or the control centers of computers, and actually of so much more than computers today. Cell phones, cars, airplanes. And if you were able to attend Professor Schambach's talk last month, you're already an expert on this. But if you weren't here, I'll do a quick 5-minute review. So let's look at the integrated circuit. Okay. Integrated circuits are found everywhere. I have some pictures up there, and if I can figure out how to use the camera, we'll look at some here as well. All right, these little black widgets inside, those are integrated circuits. I'm going to put them up here so everyone can see, hopefully. All right. And what's this? Yeah, USB memory stick, flash memory stick. This has a plastic case so you can see inside. There's integrated circuits in here. Again, the black rectangles. So let's put that here and maybe figure out how to zoom. Well, I'm going to hope you guys can see that. I'm at a disadvantage being up front. All right, so again, the integrated circuits are the brains. They're inside just about everything we use today. And so what happens if one of these, and that didn't work so well. Right, so what happens if an integrated circuit fails? And I'll pass these around so you can take a look. Again, these black rectangles, those are integrated circuits. We'll pass this on this side. Alright, so if an IC fails, is that a big deal or is that something really dangerous? Let's consider. Okay, your iPod has integrated circuits inside. Your calculator has integrated circuits inside. So if one of them fails, if one of them stops being reliable and your iPod doesn't play music anymore, or your calculator doesn't give the right answer when you add two numbers together, that's not going to kill you. It's not a matter of life and death, but you're going to be pretty darn annoyed. And actually, if you're young and you're taking a test at school, you're probably going to be more than just a little annoyed if your calculator fails. All right, now consider this. Airplanes, cars, they have integrated circuits inside. The navigation system for your airplane is controlled by integrated circuits. The anti-lock brakes on your car, controlled by integrated circuits. If those fail, it can be a matter of life and death. So it's very serious. Now I have one other example. Automatic teller. Automatic teller, financial transactions, all controlled by integrated circuits, by computers. So consider you go to the ATM, you take out $20. Your account balance should be lowered by $20. What if one of the chips is unreliable, makes a mistake, and decreases your balance by $2,000 instead of $20? You'd probably be a little bit upset about that. So for many reasons, we would like the integrated circuits in our life to be reliable. I think Professor Sanders has a question.
So maybe you answered, but when these things fail, do they just stop working, or do they give the wrong answer?
Okay, so that's an excellent question. He wants to know, how does a failure manifest itself? Does the IC just stop working and the screen of your calculator goes dark, or do you get the wrong answer? And the answer is yes. Both kinds of failures can occur. Which he knew the answer to that already. He's another reliability engineer. Okay, so remember those black rectangles, the integrated circuits? Well, that black stuff is actually plastic or ceramic, and it's called a package. It's just keeping the insides protected from the environment. So if we were to cut off or etch off that black packaging material, that's what we would see inside. And I think I do have some here I can show you. Look at some. All right, so let's switch back. Okay, so there's one of those black widgets, your integrated circuit, and I'm going to peel off the lid. And you see there is something inside. That square thing inside, that's called the chip. That's where the real action is happening inside. Again, the package is just used to protect the chip and also to route signals in and out of the chip. Now I'm going to ask, I have a lot of integrated circuits up here that have lids you can remove, and this one's especially cool. This is a really old Intel microprocessor with a second graphic processor chip, and you can see the two of them from here. So I'm going to ask my helper to bring these around the room so you can all take a look. Okay, so we have these chips inside the package, and these chips are almost all made from a semiconductor material called silicon, and there are two things on these chips: transistors and wires. And you all know what a wire is. In the context of an integrated circuit, we engineers usually call the wires interconnects. Means the same thing. So why do we call them interconnects? We give them that special name because those wires are all sitting flat on the surface of the chip, and they're rigid. And so we don't like to call them wires because wires, let's see if I can find a wire. Wires, we usually think that word means something bendy, like this. All right, so we use a different name, but it's the same thing. Interconnect, wire, same thing. So wires and transistors are on these chips. What is a transistor? A transistor is just a switch. Remember, a switch, when it's on, it allows something to pass by it. When it's off, it prevents that something from passing by. And that something could be cars, if the switch is the gate at a toll booth, or it could be electric current, or it could be water. And I have a picture of a very familiar switch there, your light switch. And that would be classified, it allows or blocks the flow of electric current, and we call it an electromechanical switch. And I'll show an example of another electromechanical switch in a moment. Let me hold this up first here, and then I'll use the camera. This is a little circuit, and it has one switch in it. Right now the switch is off. We're going to turn it on. The electric current will flow, and let's see what happens. Okay, so I assume everybody can read that. Says, oh, is there anyone in the audience who would like to turn the switch on? Go ahead, young woman, you raised your hand first. She was quicker to the draw than you. So she's going to turn it on, and we'll see what happens. Okay, so right now, no electric current is flowing because the switch is off. Oh, over here, come to the camera. Just switch, move it from off to on. Okay, the electric current is flowing. Yeah, and we can hear the alarms. Okay, that's an electromechanical switch. What we mean by electro means it's a switch that allows electricity to flow through it. Mechanical means it's manually actuated. That is, it's her hand that switches it from the two positions. Thank you very much for your help. All right. Oh. Okay, so transistor is another electrical switch, but it is an electronically controlled switch instead of a mechanically controlled switch. And it is a teeny, teeny, tiny switch, around miniature switch. We can fit millions or even billions of these transistors in one of those little chips that you saw. Now, and obviously they must be really small that we can fit billions of them into an area that big. I have a little analogy up here. A transistor is as much smaller than the whole integrated circuit than an ant is smaller than the Eiffel Tower. So that gives you a sense of the scale. If we want to be quantitative, we would say a transistor size is on the order of 10 nanometers, which is 1/1,000,000th of a centimeter. Okay, so we're going to, because I'm an electrical engineer, We're going to be talking about the reliability of integrated circuits in consumer electronics today. Consumer electronics are things you use in your daily life. Your MP3 player, your telephone, your TV, your washing machine, and so on. And if you use these products day in and day out, they will eventually wear out. They will eventually fail. And that is due to something called stress. A stress is a transfer of energy to the product, to the consumer electronics or the IC. And this energy shakes things loose inside the product and causes it to stop working properly, causes it to wear out. So let me show an example. And as I note up here, what can be shaken loose? Well, cables. We all know what a cable is, and I'll show you some pictures. But also atoms can be moved out of their proper position. So let's look at this. What is this?
Cell phone.
Cell phone. I'll take it apart. Okay.
You just voided the warranty.
It was already broken. And we'll look inside. I'll use the camera so the rest of you can see. Okay, so those are two parts. And I don't know how well, I will pass this around so you can see better. But I said cables can come loose. So I want you to notice we have a cable right here. This would connect to the speaker. And here, this chip which goes to the display, you see how it's, there's this ribbon cable which holds it in place, and I'm flexing it. And let's see, here's another ribbon cable on, whoops, hard to see, over there. And there's another one in here. So there's a lot of things, and this is very well engineered. This is a very well designed piece of equipment. But slowly, over a period of many years, something can work its way loose. Now, because we apply stress. So let me allow you guys to take a look. I will want this back later in the talk. So, how do things get shaken loose? We're properly using our equipment. Why would it get loose? Well, one form of stress is vibration. So let's take a look. Here's my smartphone. Putting it in my backpack. Putting my backpack on my back. Taking a run. All right, so what's happening to that phone inside there? It's being jostled up and down, up and down, up and down. Okay, what other kind of stress, what other kind of energy can be input to this system? Well, temperature, right? If we raise the temperature, we're adding thermal energy to the system, and that can help knock things loose. All right, the last one I want to talk about is electric current. That generates stress inside the integrated circuit. Now that might seem really puzzling. Wait a minute. The whole point is that we're supposed to run current through these integrated circuits and use them to do calculations and process information. That's the normal use. But I'm telling you, just using it properly is generating stress inside the IC, which will cause it to wear out. So one way things can fail, and I've alluded to this already, one source of reliability problem is broken wires. I have two examples up here on the screen. So the left is showing a bundle of wires that is found inside your automobile door, your car door. There's a computer in the dashboard, and signals get sent from the computer to your power locks, to your power windows. And those signals are carried through that bundle of wires. So now I want you to imagine, day in and day out, you are opening and closing the door. Opening and closing the door. The wires in that bundle are getting stretched back and forth and back and forth. Wait long enough, eventually something's going to break, as shown in that picture. Now, the picture on the right, that's a wire or an interconnect in an integrated circuit. And in that case, we're not applying any external mechanical stress. Nobody's going like this, but we're just using the integrated circuit. And look what's happened to that wire. You see how holes are developing on one side? That's a result of just the normal use. And really, it doesn't matter what causes the wire to break. If a wire breaks, the current can't flow through that part of the circuit. So here we go, and let me break a wire. Whoop! Okay, right, the electricity stops flowing. So that's going to be a very serious reliability problem. So let's, the really interesting one, of course, is the broken wire inside the integrated circuit where I'm not applying any external mechanical stress. How on earth are those holes developing in the line? Well, what's happening is the electric current is transferring energy to the atoms inside that wire, and the atoms are moving, and if they move in the wrong way, they leave holes behind, as shown in these pictures. So let's talk for a minute how these pictures are obtained. These is the inside of an integrated circuit, so they've removed the plastic protective coating, and then they take pictures through a microscope, so that so the camera's mounted on a microscope, and that's how you're able to see these teeny tiny wires that are invisible to the eye when it's unaided. And do I have a pointer here? Okay, so I'll use the mouse so you can see this wire has opened right here. This has opened here. There's another open. And here's a point where two wires are crossing and they're supposed to be connected, but you can see a hole is developing there. So these are all real pictures of real failures in real integrated circuits. And this phenomena where holes open up is giving two, it's the same, it's called electromigration. And some people don't like that word, so they call it metal migration. Again, two words meaning the same thing. So let's see if we can understand why these wires are developing holes in them. Wires and interconnects are made from materials such as aluminum and copper. And those materials are called conductors. That is, they easily conduct electricity through them. Now, all materials, including copper and aluminum, are made up of atoms. And every atom contains an equal number of positively charged protons and negatively charged electrons. Now, since the number of plus charges and minus charges are equal, we say the atoms are neutral. Okay, so are there a lot of atoms in a block of material? Answer is yes. I have some numbers up here. 1 cubic centimeter of aluminum contains about this many aluminum atoms. That's a 6 followed by 22 zeros. I don't even know how to say that number. All right, it's a huge number. And in all of those aluminum atoms, some of the electrons are sitting very close to their parent atom. And other ones are freely roaming throughout the entire block of aluminum. And that's actually, that's what makes a material a good conductor, that the electrons can freely roam throughout the material. Now, when current is flowing through a material, the electrons are not just moving around randomly, they're all moving in one direction. So now, I want you to consider I'm an electron, and I'm moving in this direction, and there's another one behind me moving along, and another one. And we're going to be colliding with the atoms. And each time we bump into an atom, we transfer a little bit of energy. And if you wait long enough, like a year, 5 years, 10 years, the atoms will have been pushed out of their original position. And they'll be pushed in the same direction the electrons are moving. So what happens is, in the direction that the electrons are flowing, you get a buildup of material, a buildup of atoms. And then at the other side of the wire, you get holes or voids developing. And this is what causes those metal migration failures. Okay, so I even talked about broken wires, broken interconnects inside the integrated circuit. But they can also, inside the chip, but they can also happen in the package. The interconnects in the package can fail as well. So this is supposed to show you a side view of a chip inside an IC package, and we have to connect the chip to the package. And in this case, it's done with these little balls of material. These are called solder bumps. And then here we have some photographs of solder bumps that have developed reliability problems. In this case, it's electromigration. You see how this hole is forming at the bottom of the solder bump? That's because the metal atoms have moved away due to the current flow. Here, you see this crack. This is called a fracture, and this is due to mechanical strain.
Elise, what's the scale on that photo?
Oh, I should know that. Give me a minute. These are about 100.
10 microns is the...
Yeah, these should be about 100 microns wide, and this is 10 microns, so good, I did well. So this whole distance is about 100 microns, which is going to be 1/100th of, no, 1/100th of a centimeter.
Is the failure rate proportional to the current?
To an exponent, it's a power dependence. And we will be getting to lifetime projection, but that was an X. So the more current you're passing through the interconnect, the sooner it will suffer an electromigration failure. 100% correct. All right, so there's another kind of a problem we can see in a package. So let me go back here for a minute. A lot of times we're going to have a heat sink mounted on the back of this computer chip, and that's to transfer heat out of the chip and prevent it from overheating, which would cause reliability problems. And a lot of times you're going to use a thermal epoxy to connect the heat sink to this computer chip. And due to mechanical strain, you can form cracks between the two, and then the chip sort of peels off of the heat sink. We call that delamination, and if that occurs, you're no longer going to get good heat transport or good heat removal from your chip. So that will lead to reliability problems. So both delamination and fracture type failures often are the result of temperature cycling. What I mean by temperature cycling is your electronic product, like your smartphone, is cold and then hot and then cold and then hot. Now, think about using your phone on a winter day. You're outside, talking on your phone, listening to your music. It's freezing cold outside. Remember this winter? And then you walk indoors and it's nice and warm. Well, you've changed the temperature, so that's temperature cycling. Integrated circuits even can generate their own temperature cycle. If you're playing some computer game with a lot of graphics, have you ever felt your computer gets kind of hot then? And then if it's sitting idle, it gets, it's cold. So even during when you go from busy use of a cell phone or a computer to the standby state, it gets hot and then cold and then hot again. So temperature cycling is part of the normal use, but this can lead to fractures and delamination. And it all is a result of the fact that objects change size when the temperature changes. And that might seem really bizarre to you. So you might have trouble believing me. Let's see if I can find my phone. So I'm not sure. I really promise you that if I change the temperature in the room, the size of this will change. Now, it may not be perceptible to you because it may be changing only 1/1,000,000th or 10/1,000,000th of a percent, but it is changing. And if you don't believe me, I'm going to do a quick little experiment up here to try to prove it to you. So the reason you might not believe me is although solid objects change size when the temperature changes, but by a small fraction. Gases change size by a larger proportion, about 1,000 times more than solids do. So I'm going to change the size of a gas in front of you, and hopefully then you'll believe temperature causes size changes. So what do I have on this milk bottle? A balloon. And let's pour hot water on it to raise the temperature. And what that should do is that should cause the air inside the bottle to increase in volume. Ooh, I'm doing too many things at once. Give everyone C. If you can't see, come close. So let's see what happens. I think the point has been made, okay? The air has increased in volume and it blew up the balloon. So do you believe me now? Temperature changes are I got more fun stuff to do here. Now, what will happen if we do a temperature cycle? If we go from hot to cold, what should happen to this volume of air inside? It should shrink. So let's see if that happens. Have some ice in here.
Like a good engineer, Professor Rosenbaum, you're not pouring water over the top of the computer?
I'm not going to do. Okay, this is cold water. And then I have some ice as well. Woman, would you come here? Would you hold this so it doesn't topple over? Thank you. Woo. Okay, so let's see what happens. Just give it a minute and see. Get cold, get cold. Oops. There we go. So the air is shifting. So please trust me, everything. This jar, my phone, temperature gets hotter, they're getting bigger. Temperature gets colder, they're getting smaller. And you can see the balloon's deflated. I'll leave this here. What should happen? Yeah, if the air is getting colder and colder and colder, and the balloon is shriveling more and more and more, it'll probably be partially sucked into the bottle if we wait another 5 minutes or so. So I invite you to come up and look at that later. We'll get a little bit technical for a minute here. If we change the temperature by some amount delta T, that might be say 5 degrees, the size of your object will change by some amount delta L, maybe 1 centimeter. And the two are proportional, linearly proportional to each other, and they're related by this constant alpha, this proportionality constant, which we call the thermal expansion coefficient. Now the reason we have reliability problems is different materials have different thermal expansion coefficients. So inside an integrated circuit, I have the package, I have the epoxy, I have the silicon chip. They're all made from different materials and they're all sandwiched together. As it gets hotter, they're all expanding, but they're expanding by different amounts. As it gets colder, they're all shrinking, but by different amounts. And so that creates, so the ones that get bigger are sort of stretching the ones that didn't expand as much. And if you allow your products to undergo temperature cycling for years and years and years, eventually cracks, fractures will occur.
Question, are those in proportion to their resistance, those materials?
Oh, is thermal expansion coefficient related to resistance?
No, just that list up there.
Oh, let me take a quick look. No, they're not, no, that's not an ordering of resistance. It's
What would be the best?
the best conductor on this list
Yeah.
would probably be copper. Is gold better or is copper?
Silver.
Silver. We don't use that in IC processing, so I don't know anything about that. Okay, we did that. So I've been focusing on the wires and on the packages, but actually I just want to mention this briefly, transistors wear out as well. So remember, transistors is switch. When it's off, no current passes through it. When it's on, it produces current. If you use a transistor day in and day out for, say, 10 years, the amount of current it produces decreases. If it decreases by 1% in 10 years, no problem. Everything's still going to work. If it decreases by, say, 50%, you're in trouble. Your integrated circuit's not going to be working properly anymore. So we have to worry about the transistors as well as the wires. So here's where the real, meat of my discipline comes in. We need to make sure products can last 10 years, or if they're going in space, 30, 40, 50 years. I cannot wait 10 years to determine if a product lasts for 10 years. Think about that. You could never sell anything. And the worst part would be is if I tested something, an integrated circuit, say for 10 years, and after 9 years it failed, I'd have to redesign it and then test it for another 10 years. So it could be 20 years till you get your part to market. That just absolutely wouldn't work. So what we do instead is something called accelerated testing. We stress the devices harder than they would be stressed under normal use conditions. We accelerate the wear out, and we try to determine if the parts are reliable. So how can we accelerate the wear out? We can turn the temperature up beyond the specified maximum operating temperature. We can cycle the temperature very rapidly, go cold, hot, cold, hot, cold, hot, back and forth, back and forth. That'll introduce a lot of stress. We can push more current into the device than is normally allowed. We can turn up the voltage higher than would be allowed, or we can expose the part to a very high humidity environment. So these are some of the ways we try to accelerate the wear out. So, all right, I turn up the voltage and my computer fails in 1 week. How do I use that information to determine if the computer will last 10 years under normal use conditions? That's the real interesting question we have to answer. And what we need is we need a model of the lifetime. We need to be able to project the lifetime under normal use conditions. So what I have shown here is a plot of lifetime versus voltage. And this is actual real data. This is what they're looking at is the lifetime of the insulator that is between the interconnects, between the wires in an integrated circuit. And so you see that if the voltage is low, the lifetime is long. If the voltage is high, the lifetime is short. That's the whole accelerated testing. And you see there are different curves drawn here which postulate different relationships between voltage and lifetime. And if you know which one of those curves is the correct one, you can predict the lifetime. So let's say we found there was a linear relationship between the voltage and the lifetime. You guys know a line is described by two parameters, its slope and its y-intercept. So I would do some accelerated testing and get a couple of data points, and then I would draw a straight line through them, and that would let me predict the lifetime at any voltage. The challenge we run into is under accelerated test conditions, a lot of different models look like they could be right. So here we have 4 different equations plotted, 4 different models for the wear out of this insulator, And these white bubbles are the real accelerated test data. So this data point which indicates that at about 4.5 volts, it takes the insulator 1 week to wear out. And who wants to do an experiment for more than 1 week, right? So then all the other ones, these are a couple of hours of stress time. But at this point, I don't know, is this the right curve? Is this the right curve? Is this the right curve? So one crazy person who I actually know, he's a good friend, he did these experiments for a year. And this data point is for 270 days. And you can see, oh my goodness, this curve's not right. This is the proper lifetime curve. But usually we can't do experiments for a year. So we, the reliability engineers, we have to study and understand the underlying physics of wear out so that we can develop the correct equation that will let us use this accelerated testing that I work on. And I haven't talked about yet. It's called ESD. And we'll be getting to that. But first I want to go back for a minute, and this will help us. I want you to remember what I said about conductors. In a conductor, some of the electrons sit close to the parent atoms, but other ones roam around the material. Well, it turns out in many materials, not just conductors, the electrons are not very closely bound to the atoms and can actually be removed from the material. Now, one manifestation of this is something called the photoelectric effect, which I'm mentioning only because Albert Einstein won a Nobel Prize for explaining it. And that's pretty cool. Oh, not most people, many people think Einstein got the Nobel Prize for relativity. He did not. He got it for the photoelectric effects. That's kind of cool. But what we're going to focus on is another phenomena which removes electrons from materials, and that's static. You all know what static cling is, don't you? See this poor woman here? You see how her dress is clinging to her pantyhose? Well, that has to do with static electricity in my research. And you see this little girl? She went through that plastic slide, and now her hair is standing up on end. Again, static electricity. So all these static things come from something called triboelectric charging. And to know what that is, I need to teach you some big electrical engineering word called electron affinity. This is just a measure of how tightly a material holds on to its electrons. Okay, we say how much it loves its electrons. So if I take two objects together, one with low electron affinity and one with high electron affinity, and I put them together, the one with high electron affinity is going to steal some of the electrons from the object with lower electron affinity. And then when I separate the two objects, the one with high electron affinity has extra negative charge on it. And the one with lower electron affinity, it's missing electrons, so it's now positively charged. So this is called the triboelectric series. It is a list of materials arranged from low electron affinity to high. And I want you to notice hair is up here and rubber is down there. They have pretty different electron affinity. So if we bring rubber and hair together and then apart, we should wind up with the rubber stealing some electrons from the hair. Let's see if that works. Who would like to test that for me? I would like this to be somebody with long hair and preferably fine hair. Not real thick and heavy, but fine, long hair. You'll be perfect. Come on up. Rub this on your hair in front of the audience. All over your head. We want a good, exciting demonstration. Okay, I think that's pretty good. Look at, don't straighten it up. Okay. So you see how her hairs are all sticking out now? What's happening? Well, remember, we think that her hair is now positively charged. Well, we have to study a new principle. Thank you so much. It's called opposites attract and likes repel. Her hairs have all been charged positively, the same polarity, so they're alike. they want to get apart from each other. And that's why the hair is sticking out, because the positively charged strands are trying to get away from each other. Yes?
So I have one question, like American is so dry.
This static electricity causes stress to ICs, and I'm a reliability engineer. Here are some pictures taken through a microscope of damage that has happened to integrated circuits due to static electricity. And these are, you can see holes have been created. This is due to melting or vaporizing some of the metal material in the integrated circuit. It's pretty dramatic looking, isn't it? Okay, so static charging in our normal daily life. Here are some measured typical voltages. So if a person walks across a carpet, they can develop a voltage, we call that a potential, as high as 35,000 volts. Now, how are we getting charged up to such a high potential? Well, that actually was, I just answered it. We're getting charged up. We are storing charge on our bodies. But it is possible for that charge to be removed. That is, it's possible for us to be discharged. And that's the shock you feel. So we just saw, walking across a carpet, we can build up a lot of charge on our body. And then I reach my hand out to touch a doorknob. Ouch! What I'm feeling is the current, the electricity flowing through my body, out the fingertip, into the air, to the doorknob. It's right where it leaves your body and goes into the air. That's where you feel the ouch. That's where you feel the shock. And I want you to look at this data. This is a dry day, 10 to 25% relative humidity. This is a humid day, 65 to 90% humidity. Look at how much lower the voltage is. That means we store much less charge on humid days. And that's why, say in Taiwan, you don't get shocks. But here in the winter you do, because the air is much drier. Now the problem is, if you are touching your cell phone or an IC, when one of these shocks, one of these static events occurs, the electronics can be damaged. And that's what I have to worry about as a reliability engineer. Yes, yes?
35,000 volts sounds really dangerous. Why doesn't that kill me?
Because we're big. It has to do with the volume of our body. So the IC is much, and especially the transistor on the IC, it's 10 nanometers. He's 2 meters. That's why he doesn't get hurt, but the transistor gets fried. It has to do with the size of the object the current's passing through. You go like this to clean the fingerprints off. ESD. So people like me need to protect these from people like you who clean the screens like that. So how do we do it? Well, actually very similar to the same way people protect buildings from lightning. Tall buildings will attract lightning. So we put a lightning rod on top and then have a copper pipe going from the lightning rod into the ground. That directs the static discharge current away from the people and the computers and the televisions inside the building and just safely brings it to the ground. Well, we do the same thing for integrated circuits. We include special semiconductor devices that take that static discharge current and steer it away from the sensitive transistors. Concept of the ESD protection device is it's an open circuit. It does nothing when there is no ESD, and it's a short circuit when there is. So, can you all see this little LED that's on? I'll show you the So I want the ESD device to normally do nothing, and when there's a static discharge, I want it to provide a safe path to bypass my sensitive electronics, just like that. See how I'm providing a short circuit, a different path for the current to flow, so it doesn't go through the diode. That's what we do. Now, because I knew a few of my colleagues would be in the audience, one quick techie slide. The way we really do it is we use semiconductor devices that look like that, And the IV characteristic looks like this. We have two branches. That's the blocking mode where the resistance is very high. This is the on mode where the resistance is low and current can flow. Okay, so that's the 2 seconds of electrical engineering. Last one. So as a reliability engineer, I hate static charge. It makes my life difficult. But is it all bad? If you're clever, you can use it. So clever people have used it to build copy machines and to build air filters. And what my teaching assistants are going to do, they're going to use static electricity to separate pepper from salt. So they're going to mix together a pile of salt and pepper. They're going to use static electricity to separate the pepper from the salt. And it's the same principle used in static air filters.
Suppose you put your iPhone in a 500-degree oven. What would happen?
Okay, we usually do not, and you're talking 500 degrees Fahrenheit or centigrade?
Fahrenheit.
Okay, at 500 degrees Fahrenheit, that is beyond the temperature at which we do accelerated testing. So at that point, if there's any Teflon in it, for example, it will probably have melted. Okay, so it would depend on exactly what materials are used, and I don't work for Apple, but because that's higher than we would do the testing, probably something will have melted, and you will probably have killed it. But a 200-degree oven, that's a different story. A few hours, it'll be fine. But don't do it, don't do it. You're going to be because you will be accelerating it. You will be accelerating the wear out. So instead of lasting for 10 years, maybe it's only going to last for 9 years now.
So I think we'll invite everyone up. I'd really like to thank Professor Rosenbaum for giving us a great close to the program. I hope to see you all in the fall physics series and next spring in the new building, the engineering series. If you did not get one of these, we tried something new for the last talk here. We've got some follow-up questions on the sheet. If you want to talk about this stuff at home, hopefully there's some stimulating conversation starters on this sheet. And if you have any feedback for us, please do email us at saturdayscience@illinois.edu. Thank you again, and please come on up.